what did we talk about last week? I know it's been a long time. You had 2 whole days of brain rest. So we're back! And here's the big question. Atomic radius. If we are, I'll call this atomic rad. If we're going this way, discuss this at your table, don't yell it out, what's happening to atomic radius? I heard a few tables say it's decreasing. Does that sound right to you? Yeah. Why? What's happening? Okay, go for it.
Electrons are being emitted to
Okay.
the main energy level.
Okay.
So that it's compacting more.
Okay. Anybody agree or disagree or want to add anything? That's a very good start. Have we added any additional energy levels between the nucleus and those outer electrons? No. Not if we're going across a period, because remember, period is the same as the highest main occupied energy level, so we're not adding any energy levels, but what are we adding? Essentially more points to get a grip on. So has anybody here ever done any furniture moving? Anybody ever helped out with moving? It's a miserable, miserable, thankless chore. You just better hope they give you a pizza or something in the end. Big heavy thing with no handles versus a big heavy thing with handles. That's essentially what's happening here. As we add increasing numbers of electrons on the outermost occupied main energy level without adding any additional layers, there are more points for the pull from the nucleus to get a hold on. There's more of a way to get a grip, really. So it pulls it in tighter, so you have a smaller radius. Now, what happens to atomic radius as we go down? Talk about it amongst yourselves. So, yeah, I'm thrilled, as you can tell. Okay, what happens? I heard a few people say it gets bigger. Would you agree? Okay. I like the term fluffy. It gets fluffier and fluffier. We keep adding main energy levels outside on the sort of distant fringes there. Copy, paste. And the more energy levels we add, the more what there is between the pull from the nucleus and those valence electrons. The more, what's that term? There's a technical term for this. Electron. Shielding! Yes! Do you think that's funny? Ha! I'm thinking of all the Saxon Dane battle scenes I read over the summer and shield walls, and nothing funny about a shield wall. But, you know, I suppose we can find something to appreciate in electron shielding. So yes, we add additional layers between the nucleus and those outer electrons. We shield those outer electrons from the pull of the nucleus, and the whole thing gets a little bit fluffier. Aside from the fact that we're just adding layers, they can't get quite as much of a grip on it. It's harder. It's like, you know, pulling through layers of something. Okay, well, good. So let's talk about making charged atoms. What is a charged atom called? Talk about it at your tables. Yes, it's an ion! So if we're going to make an ion, going back to sort of basic vocabulary tricks and tips, when you stick a T-I-O-N on the back of something, ionization is the process of making an ion. That's a terrible picture. I had to do what we'll call an old-fashioned screenshot. I actually had to take a photograph of the screen of my computer because this is Mr. Maples and he doesn't have access to all my files. So, ionization energy is what we're going to talk about. Because we're talking about the energy that's required to make an ion, and the process of making an ion is ionization. Basic vocabulary stuff. You kind of knew this. When we are talking about ionization energy, we're going to talk only about making positive ions. So how do you make a positive ion? Think about your protons and your neutrons. You can't change the number of protons, so how do you make a positive ion? A cation? You got to take an electron. So you know the joke about sodium, right? Nah. Well, sodium was living in a rather dangerous neighborhood, and somehow gunplay broke out, and sodium was hit. And sodium calls for help and says, "Help, help, I've been hit, I've lost an electron!" And the person on the other end of the phone says, "Are you sure?" And sodium says, "I'm positive." You can actually buy that on a t-shirt from Woot. I haven't broken down and gotten that one for myself yet. But yeah, when we remove an electron from a neutral atom, we suddenly have more protons than electrons, so suddenly we have a positively charged ion. We call positively charged ions that is a cat. I'm glad you knew that was a cat. We call positively charged ions cat ions. No kidding, that's what we call them, cat ions. How do you remember that? Here's how you remember that. I have positive feelings about cats. You'll never forget it again. If I see you on your test sitting there patting an imaginary cat in your lap while going, I will know immediately that you are summoning up the mnemonic so that you can remember that positive ions are cat ions. Positive feelings about cats. Cat ions are a terrible cat. Okay, so when we make a cat ion, when we make a positive ion, it takes some energy. There is some amount of energy that is needed to remove an electron from an atom. Try taking my cup of coffee in the morning. That's going to require a lot of energy. There's going to be a fight over this. So removing something from something is always going to require energy. We call the amount of energy that's required to remove an electron the ionization energy. It's not really all that creative. I'm rewriting this. I know it's on your slide, but I'm rewriting this because I want to pay special attention to it. The amount of energy that it takes, this ionization energy, the amount of energy that it takes to get an electron away from an atom, this IE, it varies by element. It varies based on how willing the element is to give up that electron. So let's look at a periodic table real quickly. And let's think about our concentric circles. What element is that? You can do your shortcut. It ends with a 3s1. What is it? Sodium. It's sodium. Now, we haven't talked about this explicitly. We'll talk about it a lot more as we go. There's something called the Octet Rule. You probably ran across it in physical science. Basically what it says is noble gases, they're the bomb. Everybody wants to be like a noble gas. Noble gases are the cool kid, and noble gas configuration is very, very stable. This is why they don't react. So what exactly would this here sodium atom have to do to become like a noble gas? Huh? Lose that one electron. So if we did this, cut, sodium would look just like neon. And this is where I think having done those noble gas configurations really helps, because you immediately realize what they would have to do to get to the noble gas configuration. So in the case of sodium, if it gives up that one 3s1 electron, it looks just like neon. Do you think that's a real hard sell? No, probably not. Probably not. Now, it still takes energy to pull that electron off. Not a lot, but it still takes energy because you've still got protons pulling on that electron. So there is energy required. Now let's imagine that instead of sodium, we're now talking about, what element is this? I just added one electron. It's really hard to see. I'm sorry. What is it? I don't know if that'll be any better. Maybe. Anyway. Okay, it's magnesium. So what would magnesium have to do to look like that noble gas? Lose 2. Okay, so magnesium gets rid of 1. Boom, it's like sodium. Gets rid of 2. Now it's like neon. Do you think... So let's think about this. And magnesium has 12 protons, 12 electrons to start with. Once magnesium loses 1, so starting out we had 12 plus pulling on 12 minus. Once magnesium loses 1 electron, think of this as a tug of war. What just happened? We just lost 1 team member over here. Do you think the second electron will be harder or easier to remove? Harder. Because suddenly the proton team in this sort of metaphorical subatomic tug of war is winning. Now, here's the other thing. It is slightly harder to get rid of that first electron on magnesium. Is magnesium's radius larger or smaller than sodium's? Starting off. Talk about it at your tables. When we add another electron on the outermost main energy level without adding any additional layers of shielding, what happens to the radius? It gets smaller, right? So if the radius is smaller, what does that mean about how tightly those valence electrons are being held?
Real tight.
Tighter than sodium. The smaller the radius, the more tightly those outer electrons are being held. So it is harder to take that first electron off of magnesium because magnesium's got a stronger grip on those valence electrons. As we go across the periodic table, guess what happens to the amount of energy required to remove that first electron? Let's put this up. So we said that atomic radius goes down as we go this way. I'll put this in another color. And we typically abbreviate ionization energy. As we go across here, guess what happens to ionization energy? It grows, yeah. It takes more and more energy because the smaller the radius, the more tightly they're holding those outer electrons. Where do you think you would find the highest ionization energy in each period? Talk about it at your table. Yeah, the noble gases. So there's really almost no way to get a noble gas to give up an electron. This is why they're not reactive. In order for things to react, they have to be willing to share, trade, give up, gain electrons. Noble gases really aren't willing to change anything. So you're going to find your highest IE here. What do you think is the second highest ionization energy on this chart? Remember what our trend is. Ionization energy increases as we go across. Where would you find your second highest?
17.
Group 17. The halogens. Not all that willing to give up electrons. They're more likely to gain electrons. As we go across a period in the main group, IE tends to increase. What do you suppose? So based on these two trends you're seeing here, let's talk about what happens as we go this way. So I'm going to take this and stick this here. So we know that as we go across a period, atomic radius decreases, ionization energy increases. What do you suppose happens as we go down a group? What happens, you know this one, what happens to atomic radius as we go down a group? Yeah, they get fluffy. They get fluffier and fluffier. Yes, I think it's funny to describe atoms as fluffy. So sue me. What do you suppose happens to ionization energy? So if AR is increasing, what do you suppose happens to IE? Talk about it at your table. It's consistent with the relationship you see going across periods. I hear people saying it decreases. Yeah, absolutely. The fluffier they are, the further out from the nucleus those valence electrons are, the less tightly they are held, the easier it is to strip one off. This starts to point to what we're going to observe about reactivity. So, with that, I'm a little nervous, but I'm sure it will be fine. We're going to do a little adventure in the fume hood.